Okay, children, hello. And the next topic we're going to discuss is nucleophilic acyl substitution reaction. Okay. നമ്മൾ സ്ഥിരം നമ്മൾ കേട്ടേക്കുന്നത് is nucleophilic addition ആണ്. We usually have or nucleophilic alkyl substitution. Here we are actually going to discuss a little bit different one. Why? Because basically ഒരു ചെറിയൊരു വ്യത്യാസമുണ്ട് in this mechanism. So this is mainly these are the reactions which basically are R C double bond O X. Okay, so e നമ്മുടെ acid derivatives, these all are our acid derivatives in the general formula ആണ് R C double bond Z, sorry, not X, Z. X would mean it is any halogen group. So in general, നമ്മുടെ ഈ acid derivatives, I am going to denote it by this general formula. Okay, and they are also called acyl compounds. Okay, ഇതിൻ്റെ രണ്ട് പേരാണ് നമ്മൾ ഇതിനെ പറയുന്നത്. ഒന്നെങ്കിൽ നമ്മൾ ഇവരെ ആസിഡ് ഡെറിവേറ്റീവ്സ് എന്ന് പറയും, അല്ലെങ്കിൽ acyl derivatives. Okay, now ഈ കേസിൽ ഞാൻ പറഞ്ഞില്ലേ, we are discussing on 4 different types in our syllabus. We discuss only 4 different types. That is, when Z is X, we have the halogens. Okay, that is Cl, Br, whatever, iodine, whatever you can take, and there it becomes our acid chlorides or acid bromides. Okay, when the X is replaced by OCOR dash, let's say it is a mixed, okay, then it becomes our acid anhydrides. Then when you replace it with NH2, it becomes our amides. When you replace it, when Z is actually alkyl group, no, not alkyl group, when Z is OR, right? Yeah, നമ്മുടെ esters ആണ്. It becomes esters. So now this R dash is basically our alkyl groups, different kinds of alkyl groups, and like I said, the X's are halogens. Okay, now the basic reaction what you would see of these kind of acid derivatives is where this Z is being replaced, okay, by some other nucleophile. Why I say nucleophile is because normally when you look at this carbonyl carbon, okay, this carbonyl carbon, you see that between carbon and oxygen, more electronegative is our oxygen. So because of that electronegativity difference, E bonded pairs would move more towards oxygen, and you would see that this is a nucleophilic center. ഒരു ന്യൂക്ലിയോഫൈൽ അറ്റാക്ക് ചെയ്യാനുള്ളൊരു വളരെ നല്ലൊരു സെൻറ്ററാണ്. So it is this carbon, the carbonyl carbon is always prone to nucleophilic attack. Now let's see how. So what you see is that this nucleophile is will attack here, and the Z will go as a leaving group. So in contrary, you would have studied for your aldehydes and ketones. So I'm just taking a ketone. When this R dash is equal to H, it becomes an aldehyde. അവിടെ നമ്മൾ കാണുന്നത് nucleophilic attack on the carbonyl groupil വരുമ്പോൾ you generally see that a nucleophile will come and attack, and then this bond goes here, and then ഇവിടെ ഒരു negative charge ഇതാവാൻ there is a addition, okay, of a H plus ion. So these are the kind of reactions that you see there, and we say that it is nucleophilic alkyl. It is a nucleophilic alkyl substitution or alkyl alla avada substitution avanadu. You see a reaction in which there is an addition, okay, nucleophilic addition it is a nucleophilic addition reaction there, okay. In this case, what you're seeing is it's getting substituted. So let us have a quick look into the mechanism. Only then you would get to see the difference there, okay. So I've already written down the mechanism. So here, see, a nucleophile, which is a electron rich center, comes and attacks the carbonyl carbon, okay. And here, just like what you would see, the first step is the nucleophilic addition. So you are adding the nucleophile onto the carbonyl carbon, and you would see such a intermediate formed. That is, you will see in this case here it was an sp2 carbon, okay. This sp2 carbon having a trigonal arrangement, okay. Trigonal arrangement with 120 degree angle, okay, is now becoming a tetrahedral arrangement. So you're having it going to an sp3 carbon with a tetragonal arrangement, and what you will see is that the angle reduces to 109 degree, roughly 109 degree, okay. Now the intermediate here is such that what it facilitates is, after the nucleophilic addition, it facilitates a elimination, okay, and not. So ഇവിടെ ആ intermediate formation കഴിഞ്ഞാൽ ഇവിടെ നമ്മുടെ nucleophilic addition കഴിഞ്ഞാൽ, okay, addition കഴിഞ്ഞാൽ the intermediate prefers to go for a elimination reaction, okay, and then it will eliminate our Z, okay. So the main thing is because in our intermediate you will see there is a high steric hindrance there. അപ്പോൾ ആ steric hindrance കുറയ്ക്കാൻ വേണ്ടിയിട്ട് bulky groups ഒക്കെ ഉണ്ടാവുമ്പോൾ the to even another thing is it prefers this elimination reaction. I'll come to that. So we'll talk about how the bulky group affects here, okay. Now bulky group actually affects this first step, the kinetics of the first step. So let's break down to the kinetic part. A kinetics നമ്മൾ നോക്കുമ്പോൾ nucleophilic addition reaction the kinetics is governed by the bulky groups that surround the acyl carbon, okay. So generally നമുക്ക് വളരെ കൂടുതൽ bulky group ഉണ്ടെങ്കിൽ the first step, okay, step 1, which is our addition reaction, അതിൻ്റെ rate കുറയും, okay. So there will be, because it doesn't favor it, okay. Another thing is that suppose we had electron, now if you are group, okay, was electron withdrawing groups, okay, on here, what happens is that electron withdrawing groups വരുമ്പോൾ the nucleophilicity of your carbon, okay, will increase. അപ്പോൾ ഇലക്ട്രോൺ വിഡ്രോയിങ് ഗ്രൂപ്പ് വരുമ്പോൾ ന്യൂക്ലിയോഫിലിസിറ്റി കൂടും, മീൻസ് ഹിയർ മോർ ആൻഡ് മോർ പ്ലസ് ചാർജ് കൂടുകയാണ്. സോ ന്യൂക്ലിയോഫിലിക് അറ്റാക്ക് ഇസ് മോർ ഫേവേർഡ്. സിമിലർലി ഇഫ് യു ഹാഡ് electron releasing group, then it would not easily go for this nucleophilic addition. So the first step 1 in the kinetics is governed by the one main thing, the two factors, that is, one is the bulky groups that are around my acyl carbon, and also the electron withdrawing and the electron releasing capacity of the groups, okay. Now let's talk about the step 2. So finally we formed the tetrahedral intermediate structure. Step 2, now there is where we know the difference between our nucleophilic addition and nucleophilic substitution, okay. Where you see you have similar case of aldehydes and ketones which undergo such kind of reactions. അവിടെ കൂടുതൽ aldehydes and ketones നമ്മൾ കാണുന്നത് addition ആണ്, the step 2, okay, is mainly addition. And so our step 2 factors that govern is basically the leaving group. Okay, so you have to look into the leaving group. So here the leaving group is Z. Okay, so if the leaving group is a weak base, okay, it will prefer elimination. If our leaving group is a very strong base, then it doesn't favor your substitution. So let us first see number Z. Then we have a set of leaving groups, right, in our your acid derivative. So you have, let's take the halides. Let me take the example of chloride. When chloride is a leaving group, then I have the C double bond O R group, okay, from our acid anhydride. Then I have my OR group, which is okay, which is basically from the ester. And then I have NH2, which is our amide group, okay, which is coming from our amide. So if you look at the basicity, it is increasing in this order. Okay, so who is the strongest base? NH2 negative is a very strong base, and the weakest is Cl negative. So among our acid derivatives, you will see that Cl is a very good leaving group, whereas NH2 is not so good. It's a very relatively poorer leaving group, and that is why you will see acid chlorides will undergo nucleophilic acyl substitution more readily when compared to acid amides, okay, or esters, or even our anhydrides will be moderately. Okay, now let's compare that to the nucleophilic. What about aldehydes and ketones? Why do aldehydes, in the case of aldehydes and ketones, okay, the elimination here would be mainly of either ഒരു carbanion. So because here, so if you take in the case of your aldehydes, you have to eliminate hydride ion. In the case of my ketones, you will have to eliminate our this R negative, okay, which is the alkyl, which is a carbanion. Okay, that now these two are very, very strong. They are stronger bases. Okay, they are very stronger bases, and this is not favored at all. Okay, so that is why nucleophilic acyl substitution in aldehydes and ketones are very, very difficult. You see that rather than give up this hydride and this carbanion, what it will do is it basically goes for addition. So there the reaction you would have seen is C double bond O. For example, you take it will be a direct addition. So you will see it will add on to a nucleophile and you will get R. The intermediate would be the same, and here it will move to this side. Okay, negative. You will have nucleophile here, and you will have your R dash here, and then finally you will go for an H plus addition. Okay, so you will have R, C, OH, nucleophile, and R dash. So this is what is favored, and not C double bond O NU. Okay, this is very difficult, wherein you are actually removing a R dash negative. Okay, so this is what the very important aspect of your nucleophilic acyl substitution, which is seen very prominently in acid derivatives. Now let's think about how it is catalyzed. Okay, now in general it is catalyzed very well by H plus and OH negative, that is in presence of a acid medium and an alkaline medium. Because in this what let's take each step. So what happens when it is in presence of an acid medium? In presence of an acid medium, what you would see is that, okay, I have my Z here, so this H plus would, the oxygen would take up the H plus and be protonated, Z O H, okay, and what you would have is a positive charge on our oxygen. Now when the nucleophile comes here, so what this facilitates is it increases the nucleophilicity on the carbon, okay, and here immediately the nucleophile can attack, and this will be very fast, and you will get RC nucleophile, and you have OH and Z, and this would be a partial bond here. This is the intermediate, okay, the transition state rather, okay, and then that would immediately go, you would see that this OH bond would come back, and the leaving group goes, and we get R C NU double bond O. Yeah, that's the final substituted product. Okay, now let me take it when you are doing, when this is happening in, let's take the hydrolysis. Okay, hydrolysis of acid derivative in acidic and alkaline medium. Let us look what happens there. If I have a typical acid derivative, so like we said, we have in acidic medium, it would go for protonation. I get RC double bond O H, and here it is positive, and there is Z, and I have my nucleophile here is water molecule. Okay, so this would come and attack the nucleophilic center, and this would go here, and we get this transition state where R, let me just remove this, R O H Z O, and you have my water molecule here, okay, with a positive charge. Now what happens is that the positive charge ശരിയാക്കാൻ വേണ്ടി this bond, the OH bond breaks, and then similarly here also it comes in this way, and Z goes off, and we get the product, which is R C double bond O OH, which is my acid H plus, and my HZ, and my H plus is regenerated, which is why we say it is a catalyst. So this happens very, very fast in acidic medium, that is hydrolysis happens very well in acidic medium. Now let's take what happens in the alkaline medium. Similarly, you will see it is also very an acidic medium and an alkaline medium facilitates hydrolysis at a very faster rate than neutral medium, okay, than in a neutral solution. So here, when it is an alkaline medium, you have a lot of base, okay, so this is a stronger nucleophile when compared to H2O. So again, this will come and attack here, you have this, and So this happens in alkaline medium. So you have R, CO, okay, negative charge. You have OH here, and we have the Z here, and then voila, you have your Z goes off, okay, and I have RC double bond O, OH. Now the thing is that because this is an alkaline medium, what you would see a lot of OH negative there, right? I should write it at this side, yeah. So what it will abstract this proton, and you get the carboxylate ion and water. So this is the product that you would see. So the relative reactivity towards basic hydrolysis, okay, you would see it in a decreasing order, that is, as expected, our acid chlorides have a more tendency to go for hydrolysis. Then will come our anhydrides. Then you would see the esters. Then you would see last would be the amides. Okay, so this is how we see the acyl substitution reactions of acid derivatives. Thank you.